Hello, I'm Chanyak Jong from Dongguk University GTM Lab. The paper I will review evaluating the value of LLMs in pattern-based technology intelligence toward increasing efficiency and reducing export dependency. Here's the bibliography information of the paper. The paper was registered in the Technological Forecasting and Social Change in 2026. The keyword and research objective are as follows. The table of contents is organized to match the structure of the paper. Technological demand can change rapidly due to external shock and technological breakthrough, making it difficult to predict. As a result, the capability of technology intelligence to recognize and respond to technological change has become a key factor for organization success. In this context, patterns serve as core data that reflect technological development and competitive activities and are widely used to identify technology trends, explore emerging technologies, and support strategic decision-making. However, trend pattern analysis requires substantial time and cost due to the large volume of texture, data, and technical terminology, making it difficult to efficiently generate technology intelligence. In particular, the need for the involvement of multiple experts to derive meaningful insight act as a major constraint. As an alternative to address this limitation, LLMs have attracted attention and their potential to support text-based analysis and decision-making across various domains has been increasingly recognized. Nevertheless, the practical applicability of LLMs in pattern analysis still requires systematic validation in terms of performance and reliability compared to domain experts. Accordingly, this study established two research concepts. First, whether the specific role that LLMs can perform in the pattern analysis process and what are their cost performance advantages. Second, how does the performance of LLM compare with that of domain expert, and what are the major constraints that limit their particular application. Therefore, this study structured the pattern analysis process into sequential stages and experimentally examined the applicability of LLM at each stage. Through quantitative and qualitative evaluation, this study compares performance and reliability and identifies both the strengths and limitations of LLMs. Based on this result, it aimed to provide practical guidelines for integrating LLM-based pattern analysis. As technological competition intensified, technology intelligence has been emphasized as a core capability for identifying technological risks and opportunities. Recently, it has evolved toward test mining-centered approaches that utilize large-scale R&D data such as patent and academic publication. However, conventional technology intelligence requires high expertise and intensive human interpretation, which limit its practical application. In this context, LLM has emerged as a promising alternative offering natural language-based analysis and rapid interpretation to help overcome this limitation. Patent are key data source for technology intelligence and are widely used for trend analysis and technology forecasting. However, the interpretation and use of research still depend heavily on expert evaluation, meaning expert reliance remain high despite advanced in patent analysis method. Patent analysis goes beyond simple data collection and function as a structured technology intelligence process for identifying trends, evaluating promising technologies, and discovering opportunities. Based on existing framework, this study adopts a six-step process that transforms patent data into strategic knowledge. Since the introduction of GPT-3, LLMs have demonstrated high performance in various natural language process tasks such as translation, summarization, and question answering, establishing themselves as core model in the field. In particular, through prompt-based approaches, they can perform diverse text analysis and generation without additional training, and their applicability is expanding in areas such as corporate decision-making and patent-based technology intelligence. Support effective LLM use in patent analysis. This study identified stages with high cost and reliability requirements. Technology understanding, data pre-processing, and research interpretation were bound to require high expertise and reliability, while data mining and knowledge presentation showed greater potential for automation. This suggests that early stages require careful validation, whereas LLM applicability increases in later stage of analysis. This study examined the applicability of LLMs in the six-stage patent analysis process, focusing on core qualitative tasks with high export dependence and cost. Based on expert survey, stage 1, 2, 3, and 5 were selected and experimentally tested to determine whether LLMs can reduce time and cost while maintaining required accuracy. The data mining and research utilization stage were excluded, and the analysis concentrated on key stage where particle LLM support is visible, assessing their applicability and limitation. When shown in Figure 3, this study was designed as two-stage research framework to evaluate the reliability of LLM output in the patent analysis process. In stage 1, quantitative performance evaluation was conducted for tasks where objective ground truth could be established, and in stage 2, qualitative evaluation based on domain expert preference was performed. Through this dual evaluation structure, both the objective performance of LLMs and their particular applicability within real patent analysis contexts were assessed. Absolute performance was measured by comparing LLM-generated research with actual analysis research. For patent analysis tasks where quantitative evaluation was visible, the evaluation tests include top applicant identification and applicant name consolidation. Both open source and closed source models were compared, and all models were evaluated without fine-tuning using a one-shot prompting approach repeated 5 times to calculate average accuracy. Next are the exploratory bibliometric analysis results. This study evaluated whether LLMs could accurately identify top applicants across three technological domains using USPTO data and the F1K metric. GPT-4 showed the highest performance overall. Accuracy was high in the P60C11 domain, but declined in DRAM and quantum computing with large variation across models. This research indicates that LLM performance varies by technological domain. Next, all the pre-processing results. In an applicant name consolidation task grouping 60 companies into 23 entities, performance was measured using ARI. The GPT-4 series achieved the highest accuracy and stability with an average ARI of 0.9896, while other models showed lower overall performance. This result suggests that LLM can be effectively applied to repetitive preprocessing tasks in pattern analysis. Next is the qualitative evaluation. LLM-generated search queries and cluster labels were compared with previous research results to assess relative performance. Three experts participated in the evaluation, and statistically scientific interrelated agreement was confirmed using candles. Both overall quality and detailed quality were assessed with detailed evaluation based on completeness, informativeness, and bias. Next, LLM-generated search queries were evaluated in comparison with list search queries from previous research. The result showed that the average sustainability was approximately level 2, and in most technological domains, the peer-reviewed research queries demonstrate higher performance. In the FCEV and NEV domains, LLM queries receive higher score in completeness and informativeness, whereas in the BEV and charging domain, peer research queries performed better. In addition, LLM queries showed higher bias score across all domain, and overall the research-based queries demonstrated more stable performance. Next, LLM-generated labels were compared with previous research labels for keyword cluster derived from topic modeling. The overall quality assessment showed that the average sustainability of LLM-generated label was approximately 2.5, which was higher than that of previous research labels. In particular, LLM labels demonstrate higher stability in the vehicle tire and electric vehicle domains. The detailed evaluation showed that LLM-generated label and previous research labels demonstrate similar performance across all three indications with average score of around 3. LLM label showed slightly higher score in completeness, but the difference was not statistically significant. Overall, while previous research performed better in search query generation, LLM produced similar or materially higher quality research in clustering level. LLM can be utilized as technology intelligence tools across the entire pattern analysis process, improving existing analytical performance and enabling tasks that were previously difficult to perform. Performance differences were observed across technological domain. High accuracy was shown in mature technologies, while accuracy declined in emerging or highly competitive fields. In search query generation, overall quality was lower than that of previous search queries, but some individual LLM-generated queries demonstrate higher performance. When used to generate multiple candidate queries for researchers to select from, LLM showed potential for reducing the cost of search strategy development. In the pre-processing stage, LLM showed high accuracy in applicant name consolidation tasks, but limitations were observed in reflecting up-to-date corporate information such as recent merger and acquisitions. In contrast, in cluster labeling, LLMs demonstrate similar or higher completeness compared to prior research, with particular potential for cost reduction in large-scale topic generation context. For a cost perspective, the use of LLM was significantly less expensive than conventional pattern analysis, indicating strong potential for reducing expert labor cost. However, LLM cannot fully replace expert in qualitative analysis, and a hybrid utilization strategy that considers accuracy and post-processing is required. From the perspective of RQ1, LLM demonstrated applicability and cost performance advantage in core texts such as exploratory biometric analysis, search query recommendation, pre-processing, and labeling. However, application constraints were also identified, including performance variation across technological domain and limitation in reflecting up-to-date information. Regarding RQ2, LLM showed performance comparable to export in search query generation and cluster labeling, but key limitation for practical application include performance degradation in emerging technological field and performance gap across models. In practice, LLM are most effective when used as export support tool to complement repetitive and cost-intensive text to ensure reliability and minimize bias. A comprehensive validation framework across the entire analytical process is required. A study experimentally verified the applicability of LLM across the entire pattern analysis process, their cost, performance, and their loss compared to export. Academically, it structured the pattern analysis process and identified stage-specific opportunity for LLM integration. Particularly, it provided guidelines for applying LLM in core texts such as exploratory analysis, search query generation, pre-processing, and labeling, and shown the potential to reduce time and cost through an LLM generation export validation workflow. However, this study focused on automotive technologies and evaluated on a selected key stage, which limit the generalizability of the finding across industries. In addition, performance may vary depending on model selection, prompt design, and the use of fine-tuning. Future research should expand the scope to diverse industry and systematically examine the performance and generalizability of integrated LLM utilization approaches, including different models, prompt and fine-tuning strategies, and lag-based external data integration. This concludes my review. Thank you.